Okay, so when you see first principle, the first thing we'll write is always the same, doesn't matter what is fx, is f dash x equals to lim h is approaching to 0 of any point plus a small increment h minus the y value at the first point, which point you want to investigate, and divide by h, which is the difference between the 2 points, okay, the 2 horizontal point h. So now, because we have unique rule for f, okay, so it's 3 minus h cubed. So f dash x equals to lim h approaching to 0, 3 minus x plus h cubed. Okay, that's the substitution of x plus h into the first function, minus fx. Well, your fx is very obvious, it's just 3 minus x cubed divided by h. Lim h approaching to 0. Well, what we have here is 3 minus, when you expand the cubic function, I will still keep them in a bracket. That's x cubed plus 3x squared h plus 3xh squared plus h cubed minus 3 minus x cubed. Plus x cubed, no, sorry, not minus, and then divide by h. And what we have is f dash x equals to lim h approaching to 0. Well, I can't substitute that yet because I have h as my denominator. If I sub 0, I will have denominator 0, which doesn't work. So I will do expansion again, minus 3x squared h minus 3xh squared minus h cubed minus 3 plus x cubed over h. Okay, fully expand everything. Okay, just fully expand everything. You should have that. As I said, any term without the h, it should be cancelled. If you can't, which means your calculation is wrong. So the x cubed and the x cubed needs to be cancelled. Well, I have 3 terms in the middle, which is here. Okay, 3 terms in the middle, which is here. So everything's all right. So f dash x equals to lim h approaching to 0. I can factorize the top. Well, the only common factor we have is h. So we have h minus 3x squared minus 3xh minus h squared divided by h. Can take the h out, because only if I can factorize and the h and h can be cancelled from the numerator and denominator. Now I can do substitution h equals to 0 because we no longer have denominator h. And when we can do substitution, we do not write lim h approaching to 0 anymore. So I sub that become h, becomes 0, and that becomes 0. So those 2 terms become 0. What we left only is minus 3x squared. Minus 3x squared. Okay, so that should be a question you have done yesterday. Just check your answers. Just go through what's first principle again with you. So if I want to find the instantaneous rate of change at x equals to 1, I can just sub 1 into f dash 1. That means it's negative 3. If I want to find the instantaneous rate of change at x equals to 0, I can sub 0 in, f dash 0 equals to 0. So I will have a gradient function, or called instantaneous rate of change function, or this is the gradient of the tangent. Okay, so that's f dash x. It's also the derivative function. What I have said so far, they're all the same thing. Derivative, gradient of the tangent, instantaneous rate of change, they're all the same. Okay, from this example, from this exercise, I have done two first principles. The first one I have done is here. Okay, so for this one is fx equals to x squared minus 2x. I will just write this down. Okay, x squared fx equals to x squared minus 2x. You know I can use the first principle to help me to work out the derivative, and we did so in question D. And in the end, we have an answer 2x minus 2. Okay, 2x minus 2. So we have 2x minus 2 here. And for that example here, we have fx equals to 3 minus x cubed. So f dash x I have worked out is minus 3x squared. Okay, that's my derivative, the final answer I have from the first principle. I just put those two down for you. If you have learned this, so don't worry, just keep quiet. If you haven't learned this chapter yet, just observe from the two equations what kind of pattern you can see. How the fx becomes the f dash x. Can you see any patterns, like anything you can observe? Well, this x2, well, not all disappeared. Decreasing? What decreasing? The power decreasing. Can we see that? We have seen a decreasing power. We have x to the power of 2, but that reduced to 1. If I have a power of 1, that reduced to nothing. For this side, a cubic becomes a square. Okay, that decreasing in power. How about the coefficient? How about the coefficient? What is here?
The power comes down. The power comes down to the coefficient.
Yeah, the power becomes the coefficient. Well, see this 2 here. That comes down, becomes the coefficient. See that? Well, I have a power of 1 here, like x to the power of 1. This 1 comes down to times with this 2, becomes 2, and then x disappears because it's decreasing in the power. This 3 come down here, well, meet with the negative, becomes a negative 3, and then we reduce the power. What happens to a constant?
It goes away.
Yeah, disappear, becomes a 0. Okay, a constant just simply disappear, become a 0. Let's think about why the constant will disappear. Let's think about the reasoning. F dash x is the derivative, right? It's the gradient of the function. If I have y equals to 3, why sketch this graph? I have this, right? This is the y equals to 3. What's the gradient of this function at any point? 0 anywhere. So that's why the constant just disappeared, becomes a 0. Because the gradient of a constant is just 0. Okay, it's just 0. And also, let's see why the single x will just disappear. For 2x, what's the gradient for the linear? 2, just the 2, right? The mx plus c, the m is the gradient for the linear. So that's why it just comes with a 2 here. Okay, also you can use the same reasoning. The 1 comes down and then 1 reduced by 1 is a 0. So that disappears. So I can reason by different way. Okay, I can reason by different way. So you know I can use first principle to find any gradient function for any function, right? But it's going to take a really long time. Like, look at what we have done. Like, we have done a lot. But that's before, like, very long time ago. They don't know how to do derivative yet. This is the initial method we're trying to work out. What's the derivative for all the functions? This is the most original method. Okay, all the formula after we learn is based on this one. Okay, it's based on this one. So what we find here is based on the result of first principle. And after people try to use first principle so for many times, they work out a pattern. Okay, there's a pattern. I can easily do the derivative without using the first principle anymore. So that's what I have talked about. They will realize, okay, it's a decreasing in the power, and also the coefficient becomes the power becomes the coefficient of the derivative. So we have a table here. Okay, we have a table here. This is only works for power functions, x to the power of n. Okay, this method only works for x to the power of n, like for polynomials or any power function. For a constant, the derivative is 0. I have explained that. For 3, the derivative is 0. For x to the power of n, the derivative is, we put the n in the front as the coefficient, and then we reduce the n by 1. Okay, we reduce the n by 1. So it's n times x to the power of n minus 1. That's the derivative. Okay, that's the derivative. How about if I have a coefficient k in the front? How about we have a coefficient k in front? I have k times x to the power of n. For example, what I will have is k times n times x to the power of n minus 1. Okay, so we just keep the k in the front if it's a times relationship. So k times x to the power of 2. So it's 2k times x to the power of 1. So this k will still just stay here. Okay, just stay here. Okay, that's for a single term, x to the power of n. Okay, that's a single term. That's a single term. I will just write here, single term. How about if I have like more than one terms? I add all the terms together, or I subtract all the terms. What I can do, I can derive them separately. And then adding them together. So I can derive, for example, I can derive the 2x squared first, and then I can derive the 2x, and then I can minus the result of two derivatives. Same as plus. Okay, same as plus. But what I will say here, really remember this. If I say y, how I can say that? I will use the hx. hx equals to fx times gx. Okay, hx equals to fx times gx. H dash x is not equals to f dash x times g dash x. When the two functions times together, the derivative is not separately derive them and then times them. Okay, that doesn't work. Same as hx equals to fx over gx. The derivative is not f dash x over g dash x. Okay, it's not f dash x over g dash x. So that doesn't work. Okay, that doesn't work. So when you do plus and minus, it works. Because if you try and you can see the result, it doesn't work. You can, like, why it doesn't work? Because all the plus work. When you times them, you should expand them first and then have the plus version. So therefore, it contradicts with if you derive them separately and then times them. The result is not the same. So I can do plus minus, but I can't do times and derive. Okay, show you an example. Like, for example, if I have fx equals to, you don't need to copy this, it's a wrong example. Fx equals to x plus 2, and then x squared minus 1. Okay, the derivative is not, well, if you derive this one, if you derive the first bracket, that gives you 1, right? X derive x is 1, so coefficient is 1, so it's 1. And then you derive the second one is 2x. The 1 disappeared and times them. That's incorrect. Okay, that's incorrect. You can't do this. So what you need to do instead is you need to expand the function. Make it x cubed plus 2x squared minus x minus 2. You can expand the function first. Make everything become single term, plus minus together. Okay, plus minus. And then I can say f dash x is 3x squared plus, well, this 2 can come down to times with that 2 becomes 4x. 2 reduced by 1 becomes 1. X coefficient of x is 1, so it's minus 1, and then the 2 becomes 0. Then the derivative should be that. And you can see this is different from that one. So the derivative cannot find them separately and then times them. We get that? Same as division. You can try the same thing for division, the same for the division. Okay. And also, well, we won't always have notation fx equals to something, then f dash x, blah, blah. We may also have y equals to something, okay? See this notation, y equals to x squared plus x minus 2. Then we can write the derivative as dy dx, okay? Dy dx, that's another notation. It's equivalent to f dash x. It's just the difference is what do you have originally? Do you have fx or do you have y equals to x? Say if you have h equals to 3t squared, what you will do is dh dt equals to 6t. Okay, dh dt, well, it depends on what you have. Because you don't have y and x here, it's very weird if you write dy dx. So it depends on what you have in the original function. So in this case, it will be dh dt. So it's d of the left-hand side and then over d of the right-hand side of the, like the terms, in terms of t. So it's dt. So if you have gx, then the derivative will be g dash x. If you have something z equals to some t, then it's dz dt. Okay, so that's just the notation thing we have. Okay, if we can look at the first one, how many questions do I have? Okay, I'll just do a couple of with you together, okay? So, and then you can investigate the rest, and then tomorrow we can check the answers together. So I'll just do this one with you. Be careful, do not directly write equal sign here because you're trying to derive the function. The derivative function is not the same as fx. So you need to have f dash x equals to something. So tell people the derivative is what? It's different from the fx. So what's the derivative should be for this one? 12x squared minus 2. That's correct. Easy. Okay, what's the derivative for that one? Minus 5 over 8.
Starting students, could Carol Ming of 11D please make her way to the general office? Carol Ming of 11D, please report to the general office now.
X squared. So what I will have is minus 5 over 2x cubed plus 9 over 4x squared. Okay, that's how you do it. They are easy because they are in plus minus form, they are extended, they are nice and easy. But if you have, well, I'm sure you this one should be expand first and then do the derivative. Let's see what we can do to this one. Let's have a look what we can do to this one. 2 over square root x. Well, my x can't be in the denominator. I said I can't divide by the function. I can't go fx divide by the gx. So how I can flip the x up? Y can be equals to what? 2 times what? 2 to the power of negative a half. And then plus, that's 5 to the power of what? 2 over 3. Okay, power first and then the root 2 over 3. Now I can do the derivative. I will say dy dx equals to 2 times negative a half. Okay, which is the power going down. And then times x to the power of, well, I will reduce the power by 1. If 4 becomes 3, 2 becomes 1. So it's all reduced by 1. So it's negative a half minus 1. Negative a half minus 1. What's the derivative for the second part? 0. Okay, so I don't need to really worry about that. That's a 0. So my dy dx will be negative x to the power of negative 3 over 2. Well, if I can just make into the third form, that can be minus 1 over x cubed and then a square root. If I was to put into the third form. Okay, so when you have z at the x at the bottom, you need to try to make it up first. If it's in a times form, you need to expand them first. Okay, so by flipping it from the bottom to the numerator, I will go negative power. You go negative power. Okay, so what I want you to do for the rest of the lesson is complete everything in page 7, page 8, page 8, and try first principle for example 1. Just give me 1 more minute. I'll just circle the questions. Example 1, try first principle for that function. Well, we don't do example 2, it's too complex. Just forget about it. And then complete example 3. Okay, complete example 3. That's it. Okay, so it's up to page 9. Okay, basically it's everything up to page 9 except the example 2 here. Okay, everything up to page 9. Except the example 2 here. Tomorrow lesson, I'll give you some time to work on this as well, and then we check answer in the end, like for the solutions. You have plenty time to do this. Okay, you can try that now.